Hello, welcome back to this channel. Today we're going to discuss the series and the parallel connections in S domain, which is very similar to the one we discussed in the phasors. So if you understood well for the phasor case, and today's content will be very easy cruise for you. As always, I will put a link to the Google Colab notes in the description down below. If you have any questions or comments, you're always welcome to leave your comments in the comment area. And let's get started. So today, as we did for the series of parallel connections in phasor case, we're going to have 4 video clips, and we're going to talk about the series connection in 2 video clips. One is for the equivalent impedance, and 2 is the voltage division associated with the series connection. And for the parallel connection, we're going to look at the equivalent admittance or the equivalent impedance if you want. And then we're going to talk about the current division in the 4th clip associated with the parallel connection. By the way, we're going to start the first discussion of the series connection. Right? So the series connection is if we have the 2 elements, remember how we can tell whether the elements are connected in series or parallel. Make sure you understand they are not, referring to the geometric, right? In the past, some students actually made that mistake, and they saw these 2 devices draw kind of in parallel or kind of, and then they say this is connected in parallel. No, we're talking about the electrically in parallel or series. So let's start with the series. The series, if 2 elements are connected in series, they share the same node without any third elements sharing, right? So therefore, in this case, in this example here, we did a similar one for the phasor case. Now, the difference here is the currents are in phasors, are in S domain, right? That means the Laplace transform of the time domain signals, and the impedance is here, and we use Z to denote the impedance, and instead of a function of j omega, now is a function of S, right? S is sigma plus j omega. That's the complex variable. And in this case, we can see Z1 and Z sub 1 S and Z sub 2S and Z sub 2S, they share the node B without any additional elements. So they are connecting in series. And it's the similarly Z2 S and Z sub 4S are connecting in series as well, right? But in the case of Z1 and 2, Z sub 1 and Z sub 2S, they are not connecting in series. The reason for that is connected in series, and they are not connecting in series because they share the same node A, but there's a third element, which is the current source, also sharing the same, right? So therefore, they are not connecting in series. And similarly, Z sub 3 and Z sub 4 are not connecting in series either, right? So are not connecting in series. I hope everybody can tell whether the element connected in series or not. Okay, let's look at the equivalent impedance for the series connection. In this case, I have n elements, n impedances connecting in series. That means Z sub 1 and Z sub 2 are connecting in series because they share the node, this node here without additional elements, so on and so forth. You can tell these elements are connecting in series. So as we did for the phasor case, we can write the element constant for each of the elements. I already labeled all the voltages across each element and the current through each element. And these, for each element, the voltage and current, they are following the passive sign convention. Remember, what the passive sign convention is the reference mark for the current, which the arrow points into the reference mark plus reference mark for the voltage, right? The plus sign for the voltage reference. So, or if the current reference arrow is leaving from the negative sign of the reference mark, right? So it has nothing to do with actual value or the voltage or current. It's all determined by the reference, the relative direction orientation of the two references, right? So that's the things we need to keep in mind very clear, because this thing will if you don't understand the passive sign current, you will make a mistake in terms of the negative signs. You have no idea what the power is flowing into or is drawing from the element, so on and so forth. So element constraint, and if they are following the passive sign convention, and we won't have any negative sign, right? So in this case, we have V sub 1s is equal Is times Z sub 1s, and I can write this for the second one here. Similarly, V sub s is equal I sub 2s times Z sub 2s, and I can do this for all the elements until the nth elements. V sub ns, that's equal I sub ns times Z sub ns. Now we have the impedance and the currents voltage all in S domain now. I hope you are not getting lost in this discussion, because we still have the portal. Last lecture we had the portal. What's the element constants in the S domain? How we translate from the time domain to the S domain, right? If you're getting lost, that's where you can find your way back to the time domain, or you can find out your way where you came from, right? So this is the element constraints, and also we can write the KCL. Based on the KCL, we have Is, that should be equal I sub 2s. That should be equal to all the currents we are having here, because they are connected in series, right? I hope this, although this is almost like a very obvious, but you should know the way we apply the KCL here is the leaving current from this node I sub 2s is equal to the inner currents to this node Is, right? So that's how we apply this. So and in this case we also know the KVL, and the KVL we have Vs. Let's see, we use this the clockwise direction, so the Vs is a voltage rise, right? So this is the voltage rise. Let me change the color if I can. Sometimes it's very hard to get my tablet working this once I record. Okay. So let's see, change color here. This is the voltage rise, right? And change it back. Hopefully I can do that. You try a few times. And in this case, that should be equal to voltage drops, right? So the voltage drop, we have V1s plus V2s plus plus all the voltage at Ns. And those are the voltage drops. I just want to make sure everybody know how I wrote this. So these are the voltage drops. So this is the one way of writing the KVL equation. This is probably the quickest way of getting the equation we really need, right? So now I can substitute the things I had into this equation. I'll change it back to the. So in this case, I substitute all the things I had. So I have Is times Z sub 1s, right? And I have getting a little bit low here. So I have I2, right? I2s times Z sub 2s plus I sub n s times Z sub ns. And since these currents are equal, so I replace all the I2 and I sub n, so on and so forth, by Is. So I can factor then the Is out. So that Is should be Z sub 1s plus Z sub 2s plus plus Z sub ns. Right? This is the equation for in terms of the first circuit here. If we have equivalent circuit, that means I have in in this case, I have V1, Vs, and Is are following the passive sign convention as well, right? Are following passive sign convention because this one is going into the positive terminal, right? So if you can see this and you can move the Vs here, this definitely is going into so passive sign convention. Therefore, we have Vs is equal, let's see, this is a function of S, so that we have Is times Z EQ. Z sub EQ, the equivalent impedance. And for these two, if the two circuits are equivalent, that means they have the same VI characteristics, right? So if you compare these two equations here, we have this one here, right? And we have another here. The only way we could have these two same equation is that ZEQ S is Z1 plus Z2 plus Z sub 2S plus plus Z sub NS. Right? So this is the equivalent impedance, almost identical to the one we had in phasor, right? Except now we have S in this equation rather than we had J omega in the previous one. Okay, so that's for the series connection. You have to be able to tell whether the elements are connected in series or not. If they are, we can calculate the equivalent impedance, just add all the impedance together. But you should be very clear how we get here. We use the element constraint and the connection constraints, right? Both KCL and KVL to arrive at seemingly very simple relationship here. I'll see you in the voltage division in a moment.